Okay, today's video brought to you by George. Watch George turn around when I call his name. George. Hey, don't embarrass me. Georgie. That's right, good boy. Okay, so today's video will be about someone who wrote me, one of the people obviously following, who's still stuck on stupid, if you will. Sorry, I don't have a more tactful way of saying anything besides stuck on stupid. I could make up one, but it's just too much energy for me to dial down my personality like that. Okay, so I wrote some notes here. Deflection, let's see if we get the focus in. Deflection equals loss of system equals turned into a truss. At the top here, I have indicating, and we can disregard the yellow for now. I believe the break's right about here in the canopy, and the red and yellow down here, the break in the deck. This would be indicating of the blister bar encompassing this rod here, not the other direction, obviously. I use this to help make it clear of what we're looking at. I could have used a smaller nut. I could have made a little blister bar myself. It's not relevant to this failure at this time. That's my belief. Let me do this. A little more lighting. Sorry guys. Let me see if I can amp that up. Here we go. Nope. So the backlighting is killing me. That probably will change it now. Good, yeah. So what happens? Backlighting, the camera sensor works with the lighting that's coming into the sensor. It doesn't know what I'm really trying to film. Okay. So let's prove my statement, and this will be the short video for today. Maybe I'll make another one. Right now, this system is supposed to be all in compression. As I showed you in I-beam video number 2, I believe, possibly number 3. We're at 4 now, if I'm right. I state that once you get deflection, it turns into a truss. Well, let's just show it as an I-beam. This is flat now, one-to-one surface. There is no span it has to perform under. I'm going to show you this will not perform as a truss as long as it's flat. So as long as this is flat, that is no deflection. I didn't say some. Zero deflection. It's performing as an I-beam without converting into a truss. Now I-beams can flex, right? But their flexural moment creates a. If they're flexing, this one is one sagging, they're both sagging, but one is more in compression and one's in tension. Either way, it creates a reaction at the end when you put these type of let's call them columns, right? Because it's not supposed to be a truss system, so why should I call them a truss? But if you want me to, I'll call it part of a. I can't really do that because I can't do it because I don't want you to think it's a truss system yet. This is an I-beam. This is just a web. So what happens now if I were to put weight on it? Let's see if I can zoom out and do this for you. What would happen? Per you guys' theory, they think it's a truss system. Well, when I put load down here, your theory is going to push out here now because it's acting as a truss. So it's going to push at the ends. Well, I'll push very close at the edges everywhere. So I'll push on this thing. You see it moving out? Let me see what the camera looks like. Yep. Watch right here. Let's give you an indicator. I put it right on there. I can pound on this thing. It's not going to deflect out there. It's not going to result in movement out here. That's not going to be a result. It is not transferring the loads out as in an I-beam capacity one-to-one on top of this deck. This is the deck now. This is the bottom flange. It's not transferring out there. I'm pushing on the top of the web. If you guys have it as a truss system, clearly I'm loading it. So if this was a bridge, and that's the upper deck, I'm clearly putting loads on it, right? Now you would argue, oh, well, it's going back to here now. You put your point loaded and it's going here, and it doesn't have to go anywhere. It's made its way to ground, if you will. Well, I agree, and I agree, and that's the whole thing about this becomes ground. This plate, the bottom flange, becomes the wide part of the flange, becomes the ground as long as you have no deflection. the moment you create deflection, you see what happens. The whole thing starts, both sag, and this becomes in compression, and this one becomes in tension. That is, it's stretching the bottom one and compressing the top one. If you're going to compress the top one like my hand shows, you're going to have uplift out on my thumb, and the thumb and the forefinger. Break that finger over there. If I do this, if I cause it to, each end is going to come up, right? Just by default. That's all you're looking at down here. And the sagging was reported. Looking at the NTSB reports, and I'm waiting for more details per my FOIA request, but it appears that it was they have it out 19 days beforehand that this happened. 19 days per their report. That means it was still in the impound, in the staging area. And we have cracking back here, which I showed in another video, which I can link you guys to. So anybody saying that, so I take offense to anyone saying that you shouldn't weld this. Well, you are right to one capacity, but I said this is doubling as a bar and number 11. But cheating so, because 11's all broken up at the bottom. I don't have this broken up at the bottom. So I'm actually giving it a stronger capacity than it really has in real life. This number 11, it's cracked up. If I were to do this like the real, which I will, we'll get to that. Believe it or not, I will get to that. Where I am going to do that, this would be dissected. It would be cut through because it's got a crack all the way through here, crack on the other side, transversing around. And I'm waiting for more imagery from NTSB. Hopefully they won't be greedy. Imagine once you do that, your loads then will, if 11 is all cracked up, literally cracked up, not if, it's being that's all cracked up, the loads will literally be going down the bar because they're clamped in concrete, right? If you lock it in. But that's nothing, that's insignificant. But once you take this out altogether with those cracks, those dissection of the cracks, this is gone. So now your last point of contact that's stable is here, and this has some shims on it, but it's also leaning out like that. That is, it cracked like hell is presented, but the crack like hell was already presented 19 days before, as I showed in the report show. So this is being gone, and this being pretty much gone, but it's some loads on it because the shims are on it. It's also up elevated by almost 1 inch where the tape measure, where the ruler is showing, and higher in the backside of that, but they don't show the ruler near the backside, indicating that this is deflecting upwards. So we have this deflecting upwards. So the deflecting moments are being created beyond the nodal area. The other connection here, the one connection here, so 1, 2, 3, and the canopy, the deck base diaphragm. But these two are independent at this point. The 12 and the deck diaphragm are independent. You clearly see it's dissected. And it's dissected because of the uplift. See the uplift when I do that, notice how it pulls away at the base. Gotta wait for the focus to kick in. Okay. So if I have uplift sag, it pulls away at the base. These are not moving in unison together. They're moving in unison, but their reactions are based on their ability to resist. The canopy clearly has an uplift greater than this capacity. If I weld these two together, and if I weld the end of this together and I try to deflect it up, it's impossible for them both to move together. It will have a torsion, a twisting action. As we know, if you look at beams that are loaded in the center, steel beams that are loaded in the center to failure, you get a torsion action. So I'm saying the loading in the center, the sagging, if you will, created a torsion action on the end. If you guys research steel beams and torsion action and loading in the center, this is center deflection, you'll see that they twist at the end when they're overloading before failure. And this is, so you guys can look up torsion, but this is how it would exhibit at the ends. The next couple of clips will show you how this exhibited in real life on the structure on each side, and the tape measure will even show per one side to the other, that torsion as I talked about. This indicates also why the balance is no longer, this structure is no longer in equilibrium when we see this twisted at the base of 12 higher like that. So here, just narrating over that's that twist you can find in the other videos I've made of this. This will show right by the two pieces of rebar standing up. Look at the floor of it, the top deck. It'll zoom in next right now. And it will show that crack is already present. This is right after the move, before detensioning. They had data. The next image will show that where the collapse happened between 9 and the structure, 910, and number 12, and at the canopy. So I was able to find the previous drawing, and this drawing you see 3, and in this previous drawing you see 2. 2 members of post-tensioning. So clearly they wanted to reinforce the structure and the top flange capacity. And NTSB is not talking about that reinforcement. Nobody is talking about that extra reinforcement that was done to strengthen the strong back, if you will, of the structure, the top flange. And it's broken free. This is just the transverse, the longitudinal cables. The longitudinal cables could not maintain their working capacity. So the longitudinal cables are times 6, right? And I'll start adding numbers to these also. But the cables, let's go up for you, help you see it. If they could keep this deck flat, we would be just as we're looking at here on this ledge, if you will, that it would just be just the same. There would be no deflection. But those cables, the longitudinal cables, are not able to keep the bridge flat. The deflection happens. The deflection by default, by any of you guys that think you're that want to attack me on that, if you will. So I'm talking to the attackers now. You explain to me how you can get a deflection in the center of the structure and 0 results out here. Everyone wants to say it's a truss system, and I ask you then, so your load for your truss system, without deflection being first, yet I've seen no calculations where people have done the canopy weight. Clearly you can do them. It's only concrete. It's got rebar reinforcement in it. I don't care if you take away all the concrete reinforcement out of it, the steel in it. It's got post-tensioning in it. So you guys are discount. You remove the post-tensioning out of the canopy. You remove the steel out of the canopy. Now you just got a dead weight loading onto these columns, and you say that the dead weight of the canopy, because that's what you're saying. You're not telling. No one's mentioning the deck deflection. None of the engineers out there mentioning this deck deflection, or are they mentioning the canopy deflection? They just have it as some load, invisible load, that only has the ability to push out 11. That has only the ability to push out 11. So the load is, where's this load coming from? It's from the load of the deck. Now you're telling me the truss system is lifting up, is helping support the deck together. That's not the position that this system takes. If you look at this system again and think of it now as post-tensioning, let's jump into that real quickly for you engineers. You're telling me that then these are 2 flanges, the wide flange, and this is the smaller of the flange of an I-beam. The smaller flange capacity is controlled by the post-tensioning times 4 pieces. And some reinforcement inside there. Straddling over, out here 16 feet, straddling over the center support columns. But then, and you have it having the ability to act like a truss system and push out number 11. Number 11 on its own as a truss action. Remember, these cracks happen before detensioning, so you have to address it before. Here are the reports. The reports show that the crack right here, right above the yellow, cracks. One more time. Let's go backwards if I can. Oh, I can't. Cracks were reported after shoring removal. Cracks reported after shoring removal. So, and then we have the reports bringing that up also, that the cracks were reported after shoring removal. These cracks are because the structure was deflecting. It was deflecting. You clearly can address it afterwards. There were no cracks presented, they said, but that was a lie. Per the minutes of the meeting they had, the cracks were discussed, and Denny Pate said they could not figure out why. They could not duplicate it, even with the finite element, these cracks. And with that said, he just called them spalling. Clearly they're not spalling. Clearly the cracks are presented, as I showed in the early part of this video with the fine line cracks. That they're there. Clearly they're there, presented with the data from the CEI, the inspector rather, the FIU's inspector right here. Cracks reported after shoring removal. Cracks reported after shoring removal. If you look at the CC above, there's plenty of data showing that it was shared off with different people. You know, Denny Pate seems like he's trying to cover the wrong person. It appears that Erica is the one who did most of his post-tensioning, but that hasn't been discovered yet, even though he's the ER engineer of record. It hasn't been discovered yet who exactly was responsible for all the post-tensioning. It appears Erica is. It's a lie. We saw the fine hair crack on the back of the deck behind number 12 over here on the base. I showed that in one of the previous videos. I'll link you if you do ask for it. So this is already cracked up. So for the other thing you have is the major cracks are all in here. I'm going to do a separate video of the image, one image in here that shows uplift again. Not supporting uplift, but shows uplift. This will be the image right here. Look in the far right there, the bottom base crack. See how it's elevated. This is that whole structure. It initially had a downward force, I believe. It created a shear 45-degree typical break, and then it had the uplift after that, the release. This doesn't have the capacity to push. If you think it does, it still has capacity to push. Tell me how much. As an engineer, tell me how much. So I'm going to add the diaphragm in the future videos. I'm going to add the diaphragm to this. I don't need it at this point because this is part of the steps I'm working up to show you the loading. I can put all my weight there, and until I guess since that's not anchored there, if I put it right there, that's unfair. I'm creating a moment there, so I got to put it over one of the uprights. I can put it all there and get no reaction down here. And when I put it here, it does. That's that uplift I did on another video. See it? But there's nothing between the two of them. I'm point loading it here. I can point load it here even too, and not get the slide out. You guys would argue that I'm secured there. I would not dispute that. I'm secured there to the tune of 2 bars, some minor reinforcement inside there, but the action down here didn't create. The action here there is no action here. It's from the stead span, so I'm creating basically I'm creating a theoretical fun model by putting a load there. There's none there. It's out here. The original load's out here through sagging, creating that uplift over here. So finally, I'll do this again for you for this video. Let's put that back on there. You see where the loads go? Back inside number. That would be the diaphragm, so you guys may hate not seeing the diaphragm here, but remember, this is equal with the diaphragm is equal, 12 is equal with the bottom of the diaphragm. So I can do that. Twelve has shims under it at one point. I'm going to show you how the shims interact and create a hinge point at the post-tension bar. That's in a future video, so bear with me. At the end of this video, I'm just going to leave up some clips for you guys to pause and look at. You see what's happening every time. This is just showing the reaction again. If a shim was under it, sort of giving you a teaser. Okay. You know what I like doing it. Getting your brain going first before I present. Now, this is, you can pause this. This is the data that I've already presented, I think, in the early part of the video. But there's Erica. She's the one that's responsible for some post-tensioning there that's critical. There's just, FIU saying how great they are with bridges. This is a study I showed you guys a long time ago, the United Emirates study. I presented it first, and showing you with the scale 30-to-1, basically the ratio is way off compared to what this structure did. So you can't even compare it, but it came to a 165-foot truss system, and they met not in the same plane. All right, so it's not even scaled the same. Take care, guys.